Hello everyone, I'm Keshav from the Math Club. Welcome to the first What is X talk for this semester. We have Professor Mainak Poddar from our own institute, IISER Pune, with us today, and he will discuss the fascinating field of differential geometry with all of us. After completing his PhD at Wisconsin Madison, Dr. Poddar has worked at several esteemed institutes all across the world, such as Michigan State, the University of Waterloo, IISI Calcutta, MEUNCC, etc. His research is focused primarily on the fields of differential geometry and complex algebraic geometry. The What is X Talk series aims to give undergraduate students an insight into how research in mathematics is conducted without focusing too much on the technical details. Without any further ado, let's begin.
So, what is differential geometry about? Okay, so basically, I hope that probably some of you already have some uh, familiarity with manifolds and other concepts from differential geometry, but I will sort of try to begin at the very basics, and then you are also allowed to stop me and ask me some doubts at any time, because I may be using some words that may need some elaboration. So yeah, please do feel free to stop me. Now, most of this, I'm not going to do a very technical talk, but I'll just try to give you some idea about what's behind, uh, you know, and give you some intuition of what we do in this subject. Now, this is not a new subject. It goes back a long time. And one can say that initially, I mean, the motivations were like out of practical necessities, like how do you perform calculations on spaces that are not linear, like, R2, the plane, or R3. So spaces that are not like Rn. And for example, like a sphere or the surface of a bagel or things like that. And now, of course, we need some assumptions. And one of the assumptions uh, that turns out to be quite convenient is that of smoothness. Okay, so let me try to say briefly what is a smooth manifold, and also, in contrast, what is a topological manifold. So, smooth, if you remember from calculus, like smooth functions uh, are so-called, C infinity functions. Roughly, one can say that, all derivatives of all orders exist and are continuous. This is, there is some kind of uh, uh, essentially, here we can assume our functions to be C infinity on neighborhoods. So this characterization would be fine for us. Now, so our spaces, these manifolds, are locally similar to uh, Rn, or like a part of Rn, sort of like an open set in Rn. And here is an example. So, what do I mean by similar? So, there would be like so called like charts, and this will kind of identify this an open subset of our manifold with uh, an open subset of Rn. So, I have here a typical example, the sphere of dimension 2. And I have broken up the sphere into two charts. So this blue part called U alpha, and the red shaded part, the lower part called U beta. And so I have these two maps. The charts is just some continuous, actually a homeomorphism from U alpha to an open subset in whatever Euclidean space. And I have another from U beta. And now what we have is, if you look at the intersection of the two, u alpha and u beta, on that we have some uh, induced maps. Uh, so in these I mean, from Rn to Rn, on this common part, I have some map given by these two homeomorphisms. And um, these maps are called transition maps. And if it just continuous, we get sort of a structure of a topological manifold on the sphere here. But if these are more, if these maps are uh, smooth or C infinity, so then uh, I'm denoting this by G alpha beta and G beta alpha, which is just the inverse of G alpha beta. So if these maps are C infinity, we say that, the manifold has a smooth structure. And so basically, you can do your calculations on Rn on each piece of your manifold, and you can do the calculation in Rn. And you connect these calculations by means of these transition maps. So, okay, now one basic question is like, uh, so in general, of course, a manifold will have, you cannot cover it with just two charts. You may need like a lot of charts, for instance. Uh, but uh, roughly speaking, a manifold is called compact if you can cover it with finitely many charts. And some important, foundational questions are like, okay, uh, is there a topological manifold which does not admit a smooth structure? And another foundational question is there a topological manifold that admits multiple, um, you know, non-equivalent or different smooth structures? Now, these, of course, turn out to, although foundational, they turn out to be very deep and non-trivial questions, and will indicate, I mean, some kind of, techniques and what the answers are to these questions as we proceed. Okay, so so far, are there any doubts? All right. So now the next question is basically, by calculations, what we can do is we can do calculus on these copies of Rn. And now we need something more. It turns out that to apply methods from linear algebra, uh, we can sort of look at something like the tangent spaces. So the tangent spaces, if you have a manifold embedded in some kind of Rn, then they can be just thought of as like the, you know, uh, spaces that approximate the manifold best at some given point, right? So for tangent spaces, we already have some smooth structure. uh, you need smoothness. You can't do it for continuous or topological manifolds. Now, so what happens is that I mean, basically, you can think of tangent space as a local linear approximation to the manifold. And so you can sort of do some linear algebra on the tangent spaces, but there are a lot of these tangent spaces, right? And together they form something called a bundle. So it's basically looks like a family of so the tangent bundle is basically the family of tangent spaces. Similarly, if you have your manifold inside some Euclidean space, you'll also have a normal space, so something orthogonal to the tangent space. And if you collect all those, it gives you another family of vector spaces. So this is called a normal bundle. And so, in general, you can have other kinds of vector bundles. And these bundles are kind of, sort of will give you a way to do some interesting linear algebra when it comes to manifolds. And the kind of the tangent space has like sort of local information, and how this bundle overall has some global information about the manifold. So this whole collection of tangent and normal bundles. Okay. Now, in order to do calculations, we need we need a concept of like uh, distance and angle, and that is usually given by sort of, in this uh, kind of setup, uh, you can do this by space. You can have an inner product. So on each tangent space, you will have a notion of you know uh, a length and angle. And suppose your inner products, which I'm looking as a family, it also varies smoothly. Then it is, so it's a positive definite inner product. Uh, and then in that case, it's called a Riemannian metric. Anyways, I kind of outlined here like the construction of a Riemannian metric by something called a partition of unity. Um, but I will not spend time on it right now. But if in the end, if you have any question, I can uh, go back and explain something about it. So anyways, but again, like metrics don't have to be just on tangent bundles. You can put them on any vector bundle. Okay, and for example, starting from the tangent bundle, like you can take, like in linear algebra, you can take a dual of a space, vector space, to get another vector space, and you can do this continuously, and so you can get a cotangent bundle, which is a dual of the tangent bundle, and so on. You can also take like determinants or tensor products and so on. So anyways, now once you have this, the next important concept is that of curvature. And so basically, let's talk about the surface case first. So in a surface at a point, you have various tangent directions, and you can look at curves uh, in those tangent directions. So one can make this a bit more precise. But and then you'd be looking at the curvature of those curves in those tangent directions, and then you can consider various objects like what is the maximum curvature of a curve, and the curvature of a curve is roughly related to the second derivative, okay, for a parametrized curve. And okay, so, and you can look at, if you think of it like this, so essentially what you can do is in a surface, if you have a point and you have a like a tangent direction in the tangent plane, and you can just have a um, take a norm, like a plane uh, in the R3 containing that tangent direction, and it cuts the surface along some curve, and you can look at the curvature of that curve. But you can, of course, so basically one tangent, so there is a normal, and you fix one tangent direction, and then there is an unique plane through the normal and that tangent direction, and then it cuts the surface in a curve, and you can look at the curvature of the curve. And the maximum such curvature is, and the minimum are called principal curvatures. Now, anyway, so this is still, we are talking about surface. Now, here's an example. Like here, you have a plane in R3, and I showed you like two tangent directions. And of course, for a plane, there is no curvature for these, these curves are just straight lines, and there is no curvature. However, what I can do is I can bend this plane. And when I bend this plane, like to make this shape, uh, this like part of a cylinder sort of. And now you see in the red direction there is no bending, but there is some bending in the blue direction. And so the blue guy has some positive curvature, whereas I mean, non-zero curvature, whereas the red guy does not have any curvature. And so you see this principal curvatures for this. Now, what happens when I bend this is that I can do it in such a way, of course, that lengths don't change, and also angles don't change. So this will be what is called, I mean, my metric would not be changing, but the principal curvatures would be changing. So basically, it seemed like that, the curvature depends on or how a surface is embedded inside the Euclidean space. Okay, not just on the metric. But surprisingly, if you take the uh, product of the minimum curvature, the two principal curvatures, the minimum and the maximum, that turns out to be an invariant under isometry. For example, here the minimum is zero in both cases. So the product of the maximum and minimum is still zero. So this product is called Gauss curvature or Gaussian curvature of a surface. And this is a famous result. It's called, the theorema egregium or surprising theorem. That this does not depend on the embedding. It only depends on the metric. And another way to look at this that we'll try to generalize later is that you have your surface, and you have at each point you have the normal. And what you do is you fix an orientation on the surface, and then you have the normal direction. You can sort of pick a positive normal direction consistently if you give an orientation. So now if you have such an oriented surface, uh, it's like I don't know, the rule of something like thumb. Sometimes when you calculate cross product and so on, you use this kind of uh, like how your when you put your thumb towards the normal direction, how your other fingers are bending either clockwise or counterclockwise. So anyways, okay, so that's something called orientation. But so now what we do is how to get a curvature. Well, intuitively, I mean, if we study how these normal directions are changing, how these unit normal length one normals are changing as we move over the surface, that should tell us, like, if it's more curved, then these normal directions would be changing more. And if it's flat, these normal directions, like in the case of a plane, it won't change. It would be like in one, you know, X, Y, Z direction, for instance, always. So what you do is look at the derivative of this normal. So there is a map from the surface to, like the unit normal basically is a length one vector. So you can think of it as an element of the unit sphere, two-dimensional sphere. So there's a map from the manifold to the two-dimensional sphere S2 given by these normal directions. And you can look at the derivative of this map in a suitable sense. And so the basically locally it's a map from a two-dimensional thing to a two-dimensional thing. And if you, for example, if you in some chart, you can look at the Jacobian of this, basically the Jacobian matrix, and then you take the determinant of the Jacobian matrix, and that is your Gaussian curvature. So now curvature plays a big role in geometry. Of course, we start doing all this because there is curvature. And okay, the curvature, of course, is a local invariant, like it depends just on a neighborhood of P, but it has some global impact. So we'll look at some interesting, you know, examples like the collection of all the curvature. If you look at it, it it has interesting information about the manifold itself. Okay, so here is some an old probably well-known term, Euler characteristic. So this is sort of what is called an invariant of a manifold. So like if I sort of um, deform the manifold a little, this thing won't change. The Euler characteristic does not change. And actually, if you have like a continuous map, uh, a bicontinuous map, that is like a bicontinuous bijection, so a continuous map with an inverse which is also continuous between two topological manifolds, then the Euler characteristic does not change. So what is the Euler characteristic? Now you may have seen this, that if I'm able to triangulate my, so let us talk about a surface first. So suppose you triangulate your surface, so break it up into a bunch of triangles, for instance, and in higher dimensions, you'd have to use, instead of triangles, you have to use higher dimensional simplices. The Euler characteristic is defined to be, in such a triangulation, the number of a surface, that is a two-dimensional manifold, the number of faces minus number of edges plus number of vertices. And it turns out quite remarkably that this does not depend on the triangulation of the manifold. And one has to work hard to do this, but okay, let us look at some triangulations here. I have the triangulation of the two sphere. First you look at this in a boundary of the tetrahedron, and that is bicontinuously bijective to the sphere. And so okay, and you can count faces, edges, and vertices, and you'll see Euler characteristics too. Another triangulation is like, think of it as like, bicontinuously bijective to the sphere, the cube, and you can break the cubes, squares into some triangles. And now again, if you count, you'll see it's 2 and so on. Okay. Now, what does this have to do with curvature? So first of all, there is this famous Gauss-Bonnet theorem, which says that if you take the Gaussian curvature and you integrate it, so the curvature turns out to be, something like, okay, you think of this as a function here, this curvature, and this dA is like an area on M, and once you have a Riemannian metric, it's a kind of, you have a notion of length and so on, angle, so you can define a notion of area. So anyways, on charts, it would look like sort of, some multiple of dA would be some multiple of dx dy, like what you have in calculus. Now, okay, but yeah, so for manifold, I have Riemannian metric, and that gives me a good, on the surface, a good notion of this, what is area. and I integrate, and uh, what we get is 2 pi times the Euler characteristic. And now this is for any two-dimensional, I mean, this is stated for any two-dimensional um, manifold, which is, uh, compact and without boundary, and some nice assumptions, smooth manifold. There are also higher dimensional analogs of this. Okay, but you see, this already has uh, uh, some strong. I mean, first of all, intuitively, what this means is you can deform your manifold a little bit here and there, like create a dent or a hill, or you know stretch it out or do whatever sort of things that you like. uh, However, this in total integral of so you can change the curvature locally, but the total of the curvature, this only depends on the the type, the topological type of the manifold. That is, by topological type, I mean up to the type up to existence of bijective bijection, uh, which is, I mean, anyways, I mean, you have taken probably metric spaces, and this is called homeomorphism. So up to homeomorphism. So this is, although curvature is very defined in this very um, yeah, I mean, very geometric, very local way. Somehow it has information about the manifold, the totality of it. And for example, I mean, if you have um, you cannot have a um, metric of uh, negative curvature uh, on the two sphere. So if the curvature is everywhere negative, then of course the integral would be negative. But Euler characteristic is 2, so that wouldn't be possible. So there are some restrictions that curvature is placing on the type of your manifold. Okay, so this is one of the, and this theme goes on in differential geometry. When even in higher dimensions, if I have restrictions on curvature, I have restrictions on the topological type of the manifold. And there are many interesting theorems and so on. Now, this story about Euler characteristic has another interesting facet. This is the, you know, related to so-called vector fields. So what is a vector field? I mean, just you can think of this as a continuous or a smooth family of tangent vectors on a manifold. And here I have drawn some vector fields for the sphere. I have, these circles that are parallel to the equator, and you can take, uh, sort of unit length tangent vectors along these circles. So at every point, you'd have a tangent vector. And in the end, what happens is that when you reach and you want this family, maybe I said unit length, that is wrong. If I want to have this whole thing to be continuous, I cannot have unit length everywhere. For example, as you go to uh, well, anyways, so maybe the length is sort of, you can take proportional to the length of these circles. And as you go towards the north and south pole, the lengths of these circles, of course, become smaller and smaller. And then at the north and south pole, the only way to keep this assignment of tangent vectors continuous is to have the zero vector at both north and south pole. Well, whereas on the torus, which is just the surface of a bagel, you have these families of circles, and here again you do similar kind of stuff, and you have a vector field that never vanishes. That is, you don't. This is a continuous assignment of tangent vectors, and no vector has to be zero. Now, the Poincare-Hopf index theorem, another very interesting theorem, says the number of zeros of a generic vector field on the manifold. So the number of zeros counted with some kind of multiplicity equals the Euler characteristic. So if the vector field vanishes, for example, if a polynomial vanishes, like say x squared times y plus 4 vanishes at x equal to 0, multiplicity is 2, right? So if a vector field vanishes, in that sense, you can also define some kind of order called multiplicity, and you have to count with the multiplicity. And generic sort of means that it has isolated zeros. So the vector field that you are considering should have um, isolated zeros if it has any zeros. So in any case, I mean, you see this very interesting fact how the Euler characteristic, first of all, I mean, if you can prove one of these statements, then it also shows that the Euler characteristic is a um, homeomorphism invariant or so on. But okay, so you see, very different things are kind of tied up, and so there is a mystery. And okay, so and this is, you are just seeing sort of a snapshot of something that works very general. Okay, so there are, I mean, this Poincare-Hopf index theorem generalizes in this very form to higher dimensions. The Gauss-Bonnet, you have to kind of adapt it, okay? Because in higher dimensions, curvature, uh, there are many directions where you can take sort of this kind of K. There are many, in higher dimensions, there will be many planes, and along each sort of two-dimensional subspace of the tangent space, you can do kind of a curvature, and so on. So one, you have to sort of adjust this, but there are versions that are available. But in some sense, some kind of a linear curvature, something coming from, anyways, some local thing, and bit of linear algebra and calculus is telling about the global type of the manifold. And here is, I'll go to higher dimensions of the curvature quickly, but here is another nice example. One of the proofs of the Gauss-Bonnet theorem, like, it goes through the fact that, if you have kind of given a metric, you have some sort of a notion of geodesic, which is, roughly speaking, a curve with shortest length between 2 points. Okay, and now this, if you can consider some geodesic triangles, and we're looking here at the standard sphere. And I chose a triangle, like, two longitudes, and this is like the equator, and you have 90 degrees, 90 degrees, and basically you have a geodesic triangle whose total angle is greater or equal to uh, um, 180 degree, which is greater than 180 degree. But in a Euclidean space, we know that the total angle of a triangle is 180 degree. And this is precisely happening because of curvature. And the Gauss-Bonnet theorem can be kind of, yeah, I mean, if you know how this, this angle of the triangle, total angle of the triangle depend on the Gaussian curvature, if you can figure it out, you can prove the Gauss-Bonnet theorem. Because the Euler characteristic is related to the triangulation, right? And you can just add your sort of calculation for each triangle in the triangulation all together, and certain things would cancel out nicely, and so on. There is another, interesting applications of curvature, like there is something about constant curvature geometries. And so, as I said, you see the curvature, I mean, the Gaussian curvature depends only on the metric, right? That was the theorem, surprising theorem. And so then one can look at, the geometries with constant curvature, and then in dimension, or even in higher dimensions, there are roughly three types: a curvature zero, curvature. For example, the torus is a curvature zero. Then curvature sphere is curvature. Sorry, I said something very wrong. Probably no. Yeah, it's right. So I'll come back to it. So torus is curvature zero, for instance, or the plane is curvature zero. Sphere is positive curvature, and there are manifolds which locally look like, the saddle on a horseback. And here one curve, if you look at this, the saddle point uh, on a horseback, there is one curve with the uh, U parabola, and then another curve with inverted U parabola. And these are like the principal curvatures. One of them is positive, one of them is negative, and you have, hyperbolic. So this is kind of negative Gaussian curvature, um, and so on. So there are basically these three types, and there is a theorem. Like the third type, you can model it by using this mu Riemannian metric, which is I have written down. This close to the Euclidean, but you have 1 over y squared. So problem at in a metric, the lengths become very large when you go near the x-axis because of the 1 over y squared. And well, has negative curvature and constant negative curvature. And uh, all right, so, and one theorem says that every surface is kind of quotient of such one of these three, this upper half plane. You have to avoid y equal to 0 in this, negative curvature case. So only the upper half plane, or the sphere, or the, whole plane with Euclidean metric. So there are quotients of such spaces. So any two-dimensional manifold can be realized as the quotient of such a one of these three by a discrete group of isometries. So some transformations that preserve the metric. And okay, so now one also tries for some analog of these in higher dimensions, and there are some kind of, there is not a direct analog, but there are still interesting theorems and so on. And also, yeah, there are models. I mean, the models are kind of similar, even in higher dimensions. Now we want to move one step forward. I mean, to take a big step. And before that, let me just again ask you if you have any questions.
So there's a question in the chat box.
Okay, let me find this now. Okay, there's the chat box. Can we define an Euler characteristic in 2 dimensions for polygons other than? Yeah, it is fine. I mean, you can do yeah. Can we define an Euler characteristic in 2 dimensions for polygons other than triangles? Yeah, it is fine. For example, if you look at the square, if you just, instead of triangulation, you break it up into squares, even like just the cube. And what happens is to triangulate the square, you can just add one diagonal. Now what it does, it increases number of edge by 1 and increases number of faces also by 1. And in the Euler characteristic, faces come with positive sign, edges come with negative sign, cancel out. So it's possible to, divide into I mean, you don't have to insist on triangles as such. Okay. So hope that kind of answers the question.
Thank you.
Okay. Now, here is where we take some serious look at some serious generalization. So what is curvature in general? I mean, when you go to 5-dimensional manifold, I mean, so there is a theorem which says that if your manifold has dimension n, then you can embed it in an Euclidean space of dimension like r 2n or 2n plus 1, depending on some. So, and there are examples. You cannot always embed a manifold of dimension n in Euclidean space of dimension n plus 1 if the manifold is too, complicated. So, the normal direction is no longer like one dimensional. There may be higher dimensional normal direction. So you have to, you cannot do exactly what you did for surfaces. Now, in general, what our goal was to study how this normal direction is varying. Okay, and in general, we can try to define curvature for any vector bundle, not just the normal bundle or tangent bundle. And what we need is a notion of connection or parallel transport. Now, essentially in 2 dimensions, why don't we need it? Well, there is some underlying connection or parallel transport, but we don't seem to notice it, sort of. But actually, there are many notions of connection or parallel transport. Now, what is just giving you some picture. So for example, this blue thing here is part of my manifold and I have curve. And those planes, that red planes I have drawn, is basically like the vector spaces at different points. So these are vector spaces that are making up my vector bundle. Okay, could be tangent spaces, could be normal spaces, could be other vector spaces. Okay, but suppose I start with a vector bundle. And now what I need to know is if I move along a curve, there are these various vector spaces which are called the fibers of my vector bundle. And is there a way to sort of go from one fiber to another along this curve? And in other words, I need at least a way to transport. Okay. And this is possible to do. Like I can define such notions of parallel transport. And now, actually, if I want to define it sort of in a rigorous way, I would be like, have to say sort of like you look at the overall space of the vector bundle, and there you have, it's a bit complicated, that there you have the overall space, and there, anyways, there you have to look at some horizontal directions that are sort of lift of the tangent planes. So if you look at the overall total space of the bundle, then and you look at the tangent space of the total space, or the tangent bundle of the total space, then at every point there is a well-defined vertical direction. There's the tangent space of the fiber, and the fiber is a vector space. So the tangent spaces of the fiber can be identified with the vector space fiber itself. Now I need some horizontal direction, and the choice of the tangent space of the total space has dimension, of the manifold plus the fiber. and you have some vertical direction, which is the fiber direction, but horizontal direction is something parallel and something that is what we call transversal to this vertical direction. And there is no canonical choice, there is no standard choice. But anyways, if you make such a smooth choice, and this is always possible, again, you can do this locally, and then you can glue by some smooth functions that never become negative. This is the partition of unity I kind of mentioned once in this talk. But there you go. So it's possible to do this notion of parallel transport. The thing is, now if you have a loop and you do parallel transport, do you get back, like the identity map? And the answer is in general, no. And if you have a loop in your manifold and in the vector bundle, you do parallel transport in general over even a contractible loop, some loop that bounds like a disk and you can contract gradually. Even there, you won't go back to the same point by parallel transport. And this is basically one way to think about curvature. Now, anyways, we can do this connection and curvature for any vector bundle on M. Okay. And in general, the constraints on curvature, anyways, so basically the curvature turns out to be something that takes values in the endomorphism of the fiber, sort of. I mean, at every point, because you see, like, you come back to the same thing. So, and there's a linear transformation, but there's some complication. You also have to sort of, I mean, this is not fully accurate. You're doing some kind of derivative also. So let me just say one word about this, that when you move, you have like sort of a standard notion of motion once you have the parallel transport. So anything that you can sort of take derivative with the respect to this standard motion in this yeah. And right, so in partial derivatives, you take del t and del. So there, sort of, if you move along this parallel transport line in the fiber, your derivative would be zero, and otherwise it would be non-zero. So with that notion, there is also a notion of this called covariant derivative. Now, in any case, the curvature turns out to be a two-form. Anyways, I don't want to go into like why it is a two-form. Sort of like, yeah, you need to plug in two tangent directions to get a number. And you don't get a number, but you get something taking value in the endomorphism. Anyways, whatever it is, some technical thing is going on, but you can make sense of. Let's forget all these technicalities and and so on. Now, in general, again, constraints on curvature have implications for the topological invariance of the manifold. And once again, one can put some natural restrictions on. So there are, infinitely many choice of connections. But one can put some natural restrictions and can identify sometimes even one connection under these restrictions. And one such restriction is that it respects the metric, like I talked about a derivative. And okay, so this covariant derivative you can apply on various kinds of things, even on your original metric on the vector bundle or on the tangent bundle. And if the covariant derivative of the metric is zero, then you have some very special connection. Okay, so, and it's a very natural condition. So you can put some restrictions on the connections. Now I come back to those questions that we started with. Do all topological manifolds admit a smooth atlas or a smooth structure? Like, can you cover it with this, charts with smooth transition maps? And the answer is no. And anyways, Milner gave some example a long time back, but Donaldson has work of Donaldson has given like a you know like a really a huge um, world of examples in dimension 4. So, and this is related to connections and curvature, so we'll just talk about that. And are there topological manifolds that admit non-equivalent smooth structures? And the answer to this is also yes. And for this question, so one topological manifold, but a multiple notion of smooth structures, and it's not even clear how you'd go about finding those. And the story is slightly complicated, but we'll give you a very basic outline in a little bit. But this question too was answered also by Milner first in the 1950s, and he gave examples of exotic or non-standard smooth structures on the seven-dimensional sphere. And the seven-dimensional sphere, he viewed this as there is a way to look at this as a family of three-dimensional spheres over the four-dimensional sphere. Okay, anyways, there is some it's not that hard, but not a good place to exactly show it to you. Okay, and somehow so and there is this is of course kind of a very also very interesting story. But I will come to the and now Donaldson's work combined with some earlier, some work of Friedman, uh, has produced uh, you know examples of both these things. That is the negative answer to the first question, and lots of examples for the positive in this answer to the second question in dimension 4. Okay. And so now we know that in particular that the simple manifold, the simplest manifold you can think of, R4 in 4 dimension, that has a continuum of exotic smooth structures, so non-standard smooth structures, and like parametrized by the real line, for instance. So there's so many of, and I think I so it was kind of amazing, very very mind-boggling, unexpected thing that happened. As kind of Donaldson's thesis is sort of known as like the most amazing um, kind of mathematical paper of the century or something like that, and people sort of refer to it like that. So anyway, so what is the basic out ingredient and outline of, you won't be able to see the whole picture, this is a bit more complicated, but the basic outline is that these things are hard to get directly. You cannot construct this by hand, but what one could do is that you consider some differential equations on the manifold. And now when I say on the manifold, I don't mean exactly on the manifold. It can be on some vector bundle over it, or something related to a vector bundle on the manifold. Maybe it's tangent bundle or some other bundle. But you will look at nice um, objects in those. It's like vector fields, right? As a vector fields are have something to do with the tangent bundles. So this is called like a section. Now, anyways, you look at some differential equations related to vector bundles. And then maybe if you choose your equation in a nice way, you'll get a good solution space. And then, you can look at the, study the solution space and see if it has a manifold structure or something close to it, and whether it's compact, and or whether you can find its compactification. And Well, then you look at topological invariance of the solution space, uh, and then maybe you are done. So that's like the rough idea. And the way the smooth structure enters is in the definition of these differential equations, because there you need the notion of derivative and smooth structure. So this is roughly what happens. And in particular, what Donaldson considered is the space of self-dual connections on four manifold on some principal bundle, I mean whatever some bundle on a four-dimensional manifold. And so you see, like, if one looks at the space of connections that satisfy some nice property, and then out of that space, I mean, it involves a huge amount of hard work and a lot of details, but then one can the space itself has some topological invariance, and from those, like something like Euler characteristic, for instance, I'm simplifying a little bit, but something called intersection form or something like that, which is slightly bit more complicated and so on. Anyways, not going into details. So, and from this, actually, from some pretty blunt topological invariance of this space of whatever self-dual connections. Now, just briefly, what is a self-dual connection? See, curvature, I said, is like a two form. So it's sort of like, locally like a dx dy times function for some coordinates xy, roughly. Okay. And there is a certain symmetry in the two forms of a four manifold. As I said, there is a volume given coming out of the Riemannian metric, and the volume is a four form. Like locally, it sort of looks like dx1, dx2, dx3, dx4 times some function. And if you have a two form, there's a complementary two form. Like if you have dx1, dx2, you should like to get dx3, dx4, and that is the symmetry. And there is an operator called the Hodge-Star operator that gives you this complementary form. And the property of this Hodge-Star operator is that its squared is identity. And self-dual, so if you have two forms, Hodge-Star gives you another two form, and if you repeat it twice, you'd get the same two form. And so the Hodge-Star operator, it has, being a squared identity operator, it has eigenvalues plus or minus one, and the self-dual ones are the plus ones. I know the two forms that are in the plus one eigenspace of the Hodge-Star operator. So in any case, so you have this template that works, and then there are more, things. I mean, the subject kept developing, and more things happened. Now, it's 6:15 now, so should I just stop, or I have two more slides, so I can just stop here, or I can quickly go through them.
Sir, you can continue if you want.
Okay, so I'll quickly go through them. There are some small ideas here. So all I've been
Excuse me, sir. So before you go to the next topic, I had a quick question.
uh-huh.
So
Yeah,
in the question two, which we had asked,
yeah.
what exactly do we mean by non-equivalent?
Yeah. So basically, if you have two smooth manifolds are equivalent if you have a C infinity, an invertible C infinity map from one to the other. And non-equivalent means that, yeah, there does not exist any such C infinity map, invertible C infinity map.
Okay, thank you.
Okay, all right. So now, yeah, so now let us go to some singular spaces, and some of them, most well-studied ones are algebraic varieties, and these are like solution space of a system of polynomial equations. And for simplicity, I have these examples which show you just one equation for each variety. And here you can see like two curves basically, and you see some singularity here in this now at this point and at this point. Okay, so anyways, now differential geometric ideas have long influenced algebraic geometry also, and one of the ways it does it is through this concept of linearization. And basically, what is linearization? Linear approximation. And if you look at Taylor expansion sort of like thing, you ignore things with t squared term or something like that, right? And so, of course, I mean, you have non-smooth spaces, but you still want to do some kind of linear approximation or a deformation, linear deformation, stuff like that. And you can very much in the spirit of different derivatives and differential geometry. And so in algebraic geometry, this is partly incorporated into the notion of a scheme. And in scheme, one of the things is you can use equations of this type are also used, like, some t to the k could be 0, some one variable. So t squared, etc., not 0, but just t to the k 0. So you look at some approximation of certain order, right? And if t squared is 0, but t is not allowed to be, then you are looking at linear approximations. So this idea, and in algebraic varieties and so on, what you have is the basic object is the ring of polynomial functions or algebraic functions. And then, if you have, you can, in the scheme, you can have nilpotent functions like powers or 0 and so on. So anyways, but also in general, many of the theorems of differential geometry have been generalized to algebraic geometry, and differential geometry has often provided like sort of a roadmap for algebraic geometry. So this is like, some of these ideas are so fundamental that, you can apply them for singular spaces also. And there is some relation, very deep relation with physics, and maybe, in general relativity, is formalized in terms of curvature and so on. Quantum physics that requires complex amplitudes, and so you will end up with this theory of complex manifolds. It's also a vast area, and particularly in string theory, you need something called, special type of complex manifolds called Calabi-Yau manifolds that have some strong connection to some important things in differential geometry. And there is also in classical mechanics corresponds to another type of branch of differential geometry called symplectic geometry. And the symplectic geometry, the main character is a symplectic form, which basically can convert functions into vector fields. Like a function is sort of like energy or Hamiltonian, and vector fields will tell you like which directions to move, and so that's dynamics. And the way it works is from H you can take the, like in calculus almost, you can take dH. That's the one form, because you can plug sort of a vector field into it. Now from dH, the symplectic form kind of converts it. It's a two form. It converts dH into some vector field xh by this prescription that I forgot now. Plus or minus of dH is, this is a two form. So you can plug two vector fields into it. Now the prescription is that you plug in xh is the vector field, such that when you plug it into omega, you get the one form. Like you have one more vector field to plug. So this is a one form because you can plug one vector field into it, and that should be exactly this dh. Okay, and anyway, so basically that's also a huge field, the symplectic geometry, and it has its own story, but yeah, we have no time for it today. So I'll thank you for listening, and I'll stop here and let me know if you have more questions.
A few minutes back, you mentioned that like we can construct a nilpotent element. Could you explain that bit again?
Yeah, this is sort of like when you go look at an algebraic variety. I mean, these things were at first not. This is very simple in the sense that um, in algebraic varieties, sort of you have this polynomial system of polynomial equations. So what you have is a polynomial ring, and you have certain functions. These equations give you functions that vanish on the variety. So the functions that survive, so these things that vanish, like like y squared minus x cubed, they produce an ideal. All multiples of them also vanish, all functional multiples. So they produce an ideal in your polynomial ring, and actually the functions on the variety are kind of just the polynomial ring quotient by this ideal. Okay, and the ideal comes from the equations. And now earlier you would only consider prime ideals, like at the beginning. Why would one consider some function whose power is 0 but the function is not 0? Okay, and nilpotent is like simple thing, like some function whose non-zero function whose power is 0. And all I'm saying is that well, I mean this but in the theory of schemes, which is like a generalization of the theory of varieties, you don't look at prime ideals, but you look at these weird things where, I mean, these algebras that you consider, uh, for varieties, they wouldn't have any nilpotent functions. But for schemes, you allow nilpotent functions. And one of the reasons is to be able to do things like linearization and so on, so to import the methods from differential geometry.
Okay, thank you.
Okay, then. So, all right. I mean, if you have questions sometime later about anything, you can, of course, send me an email. And yeah, thanks for listening. I hope you found this interesting. And so let me stop.